I mentioned that the pressure of a gas depends on several different factors. One of those factors is the volume of the gas. So the temperature, if we keep the temperature and the amount of gas present constant, those both affect the pressure also. So we want to just look at pressure and one other thing. Then what we find is the pressure of a gas sample will increase if we decrease the volume. The nice thing about these gas laws, as they're called, is that they make a lot more intuitive sense than most of the things we've talked about so far. So we can think about a balloon. If you have a balloon and you don't let air out, but you squish it and make it smaller, does that increase or decrease the pressure of the gas inside? It will increase it, right? So pressure and volume, we say, are inversely proportional. And this is how bicycle pumps work. You take a bicycle pump. It's basically a piston with two valves. And they are one-way valves. And so this valve will let air in, and this valve will let air out. When you lift up the plunger, you lift the piston up, you cause this volume to increase, and that causes the pressure to decrease. Then you have a pressure difference between inside and outside, and the one-way valve lets air in from outside. The atmosphere pushes air into the cylinder. Then on the downstroke, when you're squeezing this gas together, you're decreasing its volume, that increases the pressure. And it's trying to escape, and so it will escape into your bicycle tire. Any questions? Does that make sense? I can't tell. You're all in comas, I think. It's okay. The relationships between different gas properties are described by gas laws. Gas laws tell what happens, they don't explain why. Kinetic molecular gas theory explains why. These just say what happens. So the relationship between pressure and volume was discovered by Robert Boyle back in the 1600s. They were doing experiments with gases long before we had electricity or anything fancy like computers. So Boyle's Law assumes that the temperature is going to be the same and that the amount of gas is going to be the same. So you're not putting gas into this container or letting it out, and you're not having the temperature change. You're just looking at the relationship between the pressure of the gas and the volume. And so what we call Boyle's Law is that the volume of a gas and its pressure are inversely proportional. So the volume is proportional to 1 over the pressure. Well, that probably doesn't mean much to most of you, and that's fine. This is what we need to remember. This is the important one. P1V1 equals P2V2. Always makes me want to say R2D2. P1V1 equals P2V2. So the pressure under the first set of conditions times the volume under the first set of conditions is going to equal the pressure under the second set of conditions times the volume under the second set of conditions. If the pressure increases, then the volume has to decrease in order for these to remain equal. And this is the sort of thing, sort of apparatus that was used to study the relationship between volume and pressure of gases. It's called a J tube because it's shaped like the letter J. It's closed at one end and open to the atmosphere at the other. And we've got some mercury in here. So there's a gas over here, and then there's mercury. The mercury will want to go to the bottom of the tube, and if both ends were open, the levels would be equal. This level, this side would be equal to that side. But it's not open, and so you put the mercury in here, and it's going to squeeze this gas, but it will only squeeze it so much. So the gas is pushing on this side of the mercury, and the atmosphere is pushing on this side of the mercury. We can measure the difference in pressure by the difference in the heights of the columns of mercury. So with a ruler, we've got a piece of glassware, we've got some liquid mercury, and a ruler. This was simple stuff, but they learned an awful lot from it. Well, what happens if you put more mercury in there? This mercury is pushing down, and it's going to compress the gas, but we can still look at the difference in pressure as the difference in the heights of the column of mercury. Now the pressure is increased, the gas volume has decreased. You see that? This is what a graph of the results would look like. Here's the volume of the gas in liters versus the pressure. So what we do is we change the pressure by adding mercury, so we're going from low pressure to high pressure, and measuring the volume, and so we go from high volume to low volume. As the pressure increases, the volume decreases. So here's some data that I made up. So there's the curve that you would see if you graph volume versus pressure. Curves like this are hard to deal with, hard to predict, and so what we try to do is we figure out, well, how can we make that into a straight line? Well, if we graph the volume versus 1 divided by the pressure, the reciprocal of the pressure, now that data turns into a beautiful straight line. And that is the relationship. The volume and the pressure are linearly related. As one goes up, the other goes down. Kinetic molecular theory explains Boyle's law. So let's look at this cylinder, and we have a weight on top of it, and we have a little pressure gauge here to measure the pressure. The volume of this gas sample is 1 liter, and the pressure is 1 atmosphere. If we put a heavier weight on this movable lid, it's going to press down, and it's going to make the volume smaller, and we see that it increases the pressure. So the volume has been cut in half, from 1 to half. The pressure has doubled. It's gone from 1 to 2. That's that inverse relationship. Why does it do this? We've got the same number of gas particles in both. They're moving at the same speed, but because the volume of this container is less, those particles are going to run into the walls more frequently. Think about a bunch of kindergartners who just had sugary cupcakes for somebody's birthday, right? And let's say we've got 10 kindergartners in this room without the chairs, and we just let them run loose. They're going to run into each other, and they're going to run into the walls, right? Now, what if we make them come up and just be behind the podium here, and they're running around? Are they going to run into stuff more often? Same number of kids running at the same speed? They're going to run into stuff all the time. More frequent collisions means more pressure. Does that make sense? Maybe it does, maybe it doesn't. So we're going to do calculations. So here's the question. A cylinder equipped with a movable piston has an applied pressure of 3.0 atmospheres and a volume of 5.0 liters. What is the volume of the cylinder if the pressure is decreased to 2.0 atmospheres? This is a container like the ones we've been looking at, like this, where the size of the container can move. It's a little bit like a syringe. The lid goes up or the lid goes down. Well, we know this is a Boyles Law problem because it says Boyles Law and gives the equation right there at the top. But we're going to learn some other laws as well, and so we need to learn how to take these words and numbers and pull the numbers out and apply them to the correct equation. So what I'm going to encourage you to do is learn how to make a little table to keep track of this information. So I'm going to make a table here. So I have condition 1 and I have condition 2. And it doesn't matter which you choose as 1 or 2, but you just need to be consistent. So I'm going to read through the question again. Cylinder equipped with movable piston, applied pressure of 3 atmospheres. Okay, there's my first number. I'm going to write it in my table, and I'm going to write the unit. What kind of a measurement is that? Is it temperature? It's pressure. It actually said pressure, didn't it? And if it didn't say pressure, the unit atmosphere should tell us that it's a pressure. So I'm going to label this column P for pressure. Pressure of 3 atmospheres and a volume of 5.0 liters. Those two go together, this and that. So 3.0 atmospheres and 5.0 liters. And that's a volume. It says volume, and we know that liter is a unit of volume. I made my table too big. Let's fix it up there. And we move on. What is the volume of the cylinder if the pressure is decreased to 2 atmospheres? Okay, 2 atmospheres is the new pressure. There's been some change. We decreased it. And so 2 atmospheres, I want to put that in the pressure column because it's a pressure. And then I have a blank. I've used up all the numbers in the problem, and I have an empty square. What's the question? What is the volume? When the pressure changes, the volume's going to change. So this is our unknown volume. And I'm going to call that V2 because it's in row 2 and it's in the V column. This is pressure 1. This is volume 1. This is pressure 2, and that's volume 2. All nice and organized. Now I need the equation that relates pressure and volume. So that's Boyles Law. And I'm not going to make you remember Boyle's name connected with P1V1 equals P2V2. I'll talk about him, but I have a hard time remembering that. And I don't see the importance of it. There's the equation. Now here comes the little bit of algebra again. We need to rearrange the equation. What are we looking for? We're looking for V2. So we need to rearrange this equation to get V2 by itself on one side. There aren't any fractions here, so that's nice. So I'm going to divide this side by P2, because P2 divided by P2 is 1, and poof, it cancels out and goes away. I have to keep this an equality, though, and so if I do something to one side, I have to do it to the other side. So I'm dividing both sides by P2. I'm going to rewrite this so I don't get confused. Be careful, it's really easy to get the 1s and 2s backwards. So V2 equals P1 V1 over P2. This is not the only way to solve problems like this, but it's what I'm going to use.
You just do it straight across and just plug in the variables. P1, V1, P2.
You could plug the numbers in, yes. I don't recommend that. One semester I thought, well, let's try that. It didn't go well. Once you plug the numbers in, rearranging it is more difficult. And so you're doing some multiplication, you're writing a number down, you're dividing by another number. Every time you mess with the numbers in your calculator or rewriting them, you have an opportunity to make a mistake. So you can do it that way, but I don't recommend it. So I've rearranged the equation, and now I'm just going to put my numbers in. So I look at this table, and need to be careful to not go into the wrong classroom. I should lock the door. Then they wiggle the knob. Be careful that you get the right numbers. So this is P1. P1 is 3.0 atmospheres. Write the units. You should always put the units in there. Always. Times V1. So here's V1. Times 5.0 liters. And this is divided by P2, which is 2.0 atmospheres. Before I get out my calculator, I'm going to look at the units and see if they cancel out or what happens to them. Well, I have atmospheres here and atmospheres down here. And so just like variables, those cancel out. So now I can use my calculator. 3 times 5 divided by 2, which, if I was real clear-headed, I could do that in my head, but that's kind of risky sometimes. 7.5, and the unit that's left is liters. Okay, so the new volume is 7.5 liters. Now we should ask ourselves, does it make sense? So we have this container, a cylinder that can change volume, and it was at 3 atmospheres, and we reduced the pressure. We made the pressure less. Do we expect the cylinder to get larger or smaller? Larger. If the pressure goes down, it's not pushing as much, and the cylinder will get smaller. No. What happened to my brain just now? Did it fall out? Yeah, the pressure's decreased, the volume goes up. One goes up, the other goes down. So volume goes up because pressure goes down. Yeah. We'll ignore that. Boyles Law has applications in scuba diving. There's a very good reason that in order to go scuba diving, you have to take all sorts of classes and get certified and stuff. It's really easy to kill yourself if you don't understand what you're doing. Okay. Do you know someone who killed themselves scuba diving? No? Okay. Because that really wouldn't be funny, would it? So for every 10 meters of depth, so for every 10 meters you go down under the water, you experience an extra 1 atmosphere of pressure. It might not seem like a lot, but it is. If you've ever gone swimming and gone down to the bottom of the swimming pool when you have an ear infection, it hurts because it's putting pressure on your head, right? Well, your lungs need pressure to expand and contract. And so down here, if the pressure of the air that you're breathing, do you ever see those, like the Flintstones where they hid in the water and they're breathing through straws? How far could you go down and do that? Turns out not very far. Because if you have 3 atmospheres of pressure on your lungs and only 1 atmosphere of pressure from up here, you're not going to be able to expand your lungs and take a breath. So we need the pressurized air in the scuba tank. We need the pressure to go up as we go down so that we can still breathe. But when you're coming up, you got to be careful, because if you don't turn the pressure down, then you've got way too much pressure in your lungs. If you hold your breath as you're coming up, you'll retain that 3 atmospheres of pressure as you come up, and that's going to do some internal damage. So let's look at this example. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. We might ask, why does he do this? We don't know. He just does, and we have to deal with it. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? Does this look like a yucky problem? Yeah. Purple, because aliens don't wear hats, right? That's the answer? That'd be a decent guess. We can do this. We're going to read through it, we're going to pick the numbers out, and we're going to try to make sense of it. So, snorkeler takes a syringe filled with 16 milliliters of air. 16 milliliters. Well, we better write that down. So I'm going to make my table here. 1 and 2. So 16 milliliters. What is that? I almost said it. It's the volume, right? The volume of the air. So that's a volume. 16 milliliters of air at the surface where the pressure is 1 atmosphere. So this air sample is 16 milliliters at 1 atmosphere of pressure. So 1.0 atmospheres. And this time I didn't make my table big enough. That's the pressure. Now he takes it down to an unknown depth. The volume at that depth is 7.5. You see that something has changed? He had the air in this syringe at the surface, and now he dives down, and we're told that it has a new volume. The volume changed. So 7.5 milliliters is the volume. Okay, this is encouraging because we have our little table here, and we have all but one blank filled in. What is the pressure at this depth? This blank is for pressure, right? It's in the pressure column. I'm going to call that P2. The rest of it, just set aside for now. Let's answer this first question first. So we have volume and pressure, and so we're going to use Boyles Law. P1 V1 equals P2 V2. Here we're solving for V2. No, P2. I knew that. Solving for P2. So I want to get rid of V2. So I'm going to divide by that, so those cancel out. I also have to divide the other side. That looks like an R. It's not an R. It's a P. So pressure 2 is equal to pressure 1 times volume 1 divided by volume 2. And I'm going to take my numbers and plug them in here. Pressure 1 was 1 atmosphere. Volume 1 was 16 milliliters. Volume 2 is 7.5 milliliters. Check out the the units. Milliliters cancel milliliters. You really need to write your work out. Okay, you really need to write it out like this, and you should label your variables. Because then, if you come up with the wrong answer or an answer that doesn't make sense, you can go back and look at what you did and fix it instead of starting over. I'm not a big fan of starting completely over. Okay, so now the calculator says 1 times 16 divided by 7.5. That is 2.133 repeating atmospheres. So for sig figs, that would be 2.1 atmospheres. Well, if the pressure increases an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? I wouldn't do this to you on an exam. 1 atmosphere for every 10 meters is a conversion factor in disguise. 1 atmosphere per 10 meters. It increases 1 atmosphere. How much has the pressure increased from the surface to where it is now down in the water with the snorkeler? 1.1. So we started at 1.1 and we went, we started at 1.0 atmospheres and we have gone to 2.1 atmospheres. Oh my goodness. I can't make a decimal point today. We really should stick the 3 in there, but I'm feeling lazy. That's a difference. So the pressure has increased by 1.1 atmospheres, the difference between those. So if I take 1.1 atmospheres and I use that conversion factor, 10 meters per 1 atmosphere, that would give us 11 meters. So the snorkeler is at a depth of 11 meters. So that last part is good. It's the first part that's really, really important. Any questions?